Okay, I can understand that there's a greater opportunity for IoT. Yes, it's as revolutionary as when internet came. That's how IoT would blow into the country or blow into the world as it is. Yeah, that's exactly what it is. It's the future actually. Some of those things we watch in movies, those future-based movies, are beginning to draw closer to reality. Okay, before others joined us, I said today we're going to have an interactive class. So I'm unmuting everybody so that you can talk. Although I'm going to mute the one person whose environment is noisy so that others can hear very well. I'm asking the question of what drew you guys to IoT? What brought you to IoT? What was the motivation behind choosing IoT? And Samuel said that it's going to be something that will bring more opportunities to the youth. It's the internet of the future. Okay, can I get more feedback from the rest of you? If you want to talk, if you want to type it, let's have an interactive class today. Good afternoon, Ahmed Adewale. Welcome to the class today. Are we all there? Can everybody hear me? Tony Peace, Ola Abraham, Obeyemi, Adeni, Aziz. Can you all hear me? Okay. Peace says to make sure Nigeria joins the IoT trend, and so that foreign companies will stop ripping us off. They are actually ripping us off, for real. Exactly. If not for countries like China, for the continent Asia, if it wasn't for Asia, we'd be buying things very costly. Close to 95 to 99% of the cars we use currently in Nigeria come from Asia. Imagine having to buy American cars or just Benz, the German cars, or BMW. Most Nigerians won't be able to afford a new one. Okay, Adeni said the world is fast changing with more sophisticated technology, so we have to be prepared. That's a very good one. If Nigeria was prepared for the revolution of the internet, we would have tapped into it earlier. Yes, we're using it now, but we should have been prepared for it, and that's one of the reasons why IoT is important. That we're learning it now is important, so that we can tap into it as it develops. Okay, I'm having interference from somebody else, so I'm meeting everybody back. Bayemi wants to ask a question. Your mic is on, Bayemi.
Oh, okay. Hello.
Yeah, I can hear you.
Okay. The only thing that I think that brought me to IoT, in this life, everybody is really internet to do another thing.
True.
And what we know,
Bayemi, I lost you there. I can't hear you anymore. Can you hear me? Can anybody else hear Bayemi talking? Okay, I can't hear him either. Since his own network has gone a bit bad. Okay. So today I'm expecting questions from you guys on the part of everything we've handled so far that is sounding a little bit too strange for you. Remember, the physical classes we're streaming it down to what is important, to the practical classes of what is important. There's a lot of things that yes, you're expected to know, but there are quite a few things that are very important that you need to understand. So you won't be hearing us dealing with things like standards and the rest of them. If you if you as an individual want to dig deeper and get to that stage, yes, we can understand it. But then we'll touch the places that are very important to getting you going, in using it to drive your success, in using it to enrich your pockets, in using it to prepare for the future. That's what we're looking at. So today's class, I'm going to be a bit fast so that I can create more time for us to do a review of everything we have looked at so far. So I'm going to talk about sensors and actuators. Actually, talking about actuators themselves. Sensors, I've talked about them before. And then I'm going to look at embedded systems. All of these are combined. Then we'll look at dynamically distributed cloud. I won't spend time on that because when we do the practical sessions on cloud, we understand what that all is about. And then finally, we'll look at IoT security. Okay, now, Bayemi, I can hear you now. We lost you there before.
Okay. Uh, my question is,
Okay.
are we going to depth into either CLI mode, and he has his own personal computer,
Yes,
or
each
can we turn it to enterprise mode?
okay, each platform, each IoT platform has its own set of rules and has its own set of operations. But the most general of them all is Arduino. The Arduino is it's a board. It's an interface or a device that helps you connect multiple sensors. Another one is the Raspberry Pi. The Raspberry Pi also is a computer of its own, but it's, let's just call it a microcontroller, but it's bigger than a microcontroller. It lets you control other devices. You know, the only thing our physical computer, these laptops and desktops, can connect to is things that can connect via USB or via the serial port and so on and so forth. But the Arduino itself, it's a board. It's like giving you a motherboard and telling you to connect anything you want to connect to it. The same thing with the Raspberry Pi. So we're going to be digging deep in Arduino. You understand the programming part of it, how to program an Arduino component, the board itself. I would make available for specialized practicals the physical boards and physical sensors so that we can do a few connections here and there. I'll introduce you to the platform where you can do personal testing. Instead of you spending your own money at the beginning buying Arduino boards and the rest of them, we have a platform where you can simulate those things. And then the enterprise part of it, turning it into a profit making. Think about it this way, that you understand the technology that drives something, and then you prepare ahead of time, waiting for that technology to be noticed, or you bringing out information, enlightening people about it. Let me give you a practical example. When the concept of IP cameras came out, cameras were existing, security was existing until people started seeing the need to keep track of security on their mobile phones in their offices. Now you understand that that particular invention, the IP camera, now became a thing. Some persons will go as far as being able to build their own system using the available sensors. So let me give you a practical example now. In an agri farm, if a farmer understands the difference in the conventional farming and the difference in the IoT based farming, using IoT to enhance farming, if he understands the profit margin, I am sure he will buy into the IoT system. Now, if you have been able to deliver on projects concerning agriculture, you've been able to understand how it works, you've been able to source out the sensors you need, the connection you need. Now, what's remaining for you is the sales part of it, selling your product, selling your idea to the average farmer. Remember, the average farmer is not that well enlightened, so yours will be like you are enlightening the person, and then you are giving the person the product, and you are helping the person achieve the success the product is supposed to give. So that's why we didn't just jump into teaching you how to using projects, just doing all the projects. You have to be able to sensitize the people you're bringing that technology into. New technology is a bit scary to people. People fear it. So you being able to explain it, break it down to pieces, is important in the entrepreneurial side of things. So we're going to be engaged in a little bit of coding. That's what I said. In sometimes we're going to do a little bit of block coding for those who don't have any coding background. Then we'll translate the block coding into physical coding as it is, into physical programming. Remember, most of those things we're talking about are already pre-configured. So you are not getting your proximity sensor and coding the proximity sensor. No, you are using the sensor to achieve a purpose. So your only coding or your only programming will come in between the device that you are using, the platform that you are connecting it to, and the task that that particular thing is supposed to do. Mr. Aziz said cannot hear me clearly. Is there any other person experiencing that issue? Okay, Aziz, your network is a bit bad then. But you understand what I'm trying to explain. The enterprises or the entrepreneurship side of our class. The entrepreneurship is you using this thing. Okay, let me see if I can give you another practical example. Currently, most states are still stuck with their regular traffic. I heard that Lagos State is trying to implement an intelligent traffic that will help people plan or help people understand how to avoid jammed areas. Now, radio stations currently do this. Usually around 3:30 to 4 p.m. in the afternoon, you hear radio stations asking people in traffic to give them a call to tell them the status of the traffic in every area. So what if that radio station can get that information from your own IoT device? What if people will subscribe to your own channel, your own app, to understand where there is traffic? So imagine you proposing such to the government and helping them deploy sensors at traffic lights or traffic points, helping them detect when the traffic is heavy, which routes to take. All of these are the entrepreneurial side of things. So you're beginning to get the idea now behind this. The one I just mentioned now is something massive. There are smaller ones, there are little ones, like helping someone configure, helping a house configure some proximity sensors, some security sensors. We already know the concept of car tracking that currently the buses and transport systems use. They track their buses to wherever destination. They install the speed limiter to make sure the buses are running at a specific speed, 100 kilometers. But these are all implementations of Internet of Things. So the more people are getting enlightened about it, the more people would key into it. Currently, did you notice that people tend to become more security conscious when they've suffered some security problem? For example, in the last 1 week, after I released a couple of videos on my WhatsApp status about security, people call me asking me questions about lost phone. If they lose their Android phone, how can they get it back? And then nobody understands that if you want to be able to track your phone, especially an Android phone, by yourself, you have to have done something about security before the phone gets missing. The persons who are licensed to track your phone via the IME number is security outfits, security offices, in collaboration with network companies, your MTN and co. An individual does not have a license to track you using your IMEI number. It's between security offices, as Nigerian police and the army and the rest of them, and telecom companies. But if you were able to install some form of security in your phone, some serious ones, then when the phone goes missing, you can track it by yourself. That's being proactive, taking an action. So you sensitizing the industry you are coming into that you want to benefit from is the first way to go about getting them to buy into your technology. We're not saying after our practical class you should carry everything, every aspect of the use case scenario and follow through. No. All the use case scenarios, you think of the one that relates to what you do. IT is in collaboration with what you already do. So if you are already someone who is into agriculture, then you are thinking of bringing IoT into the field. If you're already in the medical field, you're bringing IoT into the medical field. These are all the things that we expect that you choose one use case scenario and broaden your knowledge on that one, then push forward to achieve what you want to achieve in that section. So I hope that answers your question. By me asking about coding on the command line interface and GUI is dependent on devices we're dealing with. First of all, we're going to learn the electronic part of it, the connecting and not the connecting part of it, and then we can now deal with the networking part of it, connecting them to the cloud. Okay. So, do we have any other questions? Okay, while you are still attempting or attending to the questions, let's go straight to a few of the things we are going to achieve today. I told you I was looking at sensors and actuators. We already talked about sensors before. We've looked at sensors before. They monitor conditions, they monitor environmental conditions. They take from the physical environment and then they interpret it or they translate it and feed it to another system. Okay, that's your sensors. So what's on my display says whereas sensor monitors conditions of equipment, the actuators drive events within the equipment. So they're already talking about actuators. So actuators are actually the reverse of sensors. I don't think I need to ask you this question anymore because I've already just talked about sensors. We talked about it a couple of times. So there is little or no need of me asking you what a sensor is. Let's jump straight to what an actuator is. An actuator causes movement or action after receiving input from any other system. For example, after receiving input from a sensor. That's what your actuator would do. I hope you understand that. So an actuator causes movement or action. It takes in an electrical signal and combines it with an energy source to create motion. To create motion, to perform a task, to perform an action. That's what your actuator is all about. The second slide here says it operates in reverse direction of a sensor. A sensor reads the physical environment and translates it, while an actuator takes what comes in as an electrical signal and performs a physical action. We actually encounter actuators on daily basis. That the automatic door sensed your presence and opened the door. Now that's an actuator at work. Okay, that's like a very practical example of this. You walk close to the automatic door and it swings open by itself, or you press a button on the door and it swings open. The button itself is the sensing, then the actuator does the work. Now there are different types of actuator, all based on their operational systems. So you have hydraulic, you have pneumatic, you have electrical, thermal, magnetic, mechanical. There are so many other ones. These ones are just the very popular ones, the big platform based ones, or the big sector actuators. Your hydraulics just talks about using fluid from the word hydraulics, you should understand that hydraulic uses fluid to perform its action. It uses hydraulic power to perform a mechanical operation. They are actuated by a cylinder or a fluid motor. So that's what you get for the hydraulic systems. Somebody will just say, put your mind to hydraulic brake. When you push on the brake, then it performs the task. That's just mechanical. What I just mentioned now is mechanical. But what about pressing the button to stop, to apply brakes? Now that becomes a conversion from electrical to mechanical. You understand? Now what about a a robot sensing, or a machine sensing a presence and stops? You've heard of the autonomous cars that drive themselves. You heard of the BMW autonomous car or the Benz autonomous cars that sense what is around them and take an action. So that's sensing and actuators working. So in the hydraulic part of it, or using hydraulics, the fluids perform the action. Okay, when sensing happens, the fluid leads to what the action is. Now there are advantages and disadvantages to using hydraulics. The advantages here includes large magnitude of force. It actually provides one of the biggest kind of force you can get. There's this popular adage that says you can't stop the flow of water. Wherever it wants to go, it goes. The concept of electrical generation, generating power, hydraulic, it's fluid blocking its path, and then it generates that amount of power. It's used in welding, clamping, used in lowering and raising the vehicles in the cars, transport carriers. So you've gone to places where they use those forklift and the rest of them. They use buttons to move them. That's the sensor and actuator working. Disadvantage is that whenever you have the fluid leakage, efficiency is lost, and it's expensive, and it requires noise reduction equipment as well, and then heat exchangers just to maintain what's happening there, and it actually has high maintenance. That's the disadvantages of using the hydraulic. I'm only going to talk about three of them: the hydraulic, the pneumatic, and the electrical. The other ones are something that we can dig into at a later time and figure things out. Then the pneumatic actuator uses energy formed by a vacuum or compressed air. That's what your pneumatic is all about. It's one that is used in both robotics and the humanoids, the robots that are like humans. They don't use fluid; they use air. It has advantages and disadvantages as well. The advantages is that it's lower cost. It has a lower cost. Okay, and then they need low maintenance. They are usually durable. But the disadvantage is that once the pressure is lost, the pressure that you are building in that vacuum, once the pressure is lost, everything is almost gone. Okay, and then there should be some form of air compressor that is continuously running. Those are the disadvantages of using pneumatic. The last one here is electrical. This is the most common. This is the most common, and this provides you the most precise. This is the one that you can easily get 100%. Hello, can everybody hear me? Someone complained that the screen went off. But is it better now? Okay, he said it went off like 2 slides. Okay, so that means hydraulics and the pneumatic. Okay, so I'll go back to it. Pneumatic, I was talking about pneumatic actuators, or the fact that it uses air as opposed to hydraulics that uses fluid or water. Fluid summarizes it. Okay, so pneumatic uses air and vacuum, and I mentioned the advantages and disadvantages. The air is a lower cost option. It's very quick in starting and stopping the motion because it's a compressed air. And then whenever there's loss of pressure for disadvantage, it's less efficient. And the air compressor has to be functional. Okay, that's what I talked about for pneumatic. And then I mentioned that electrical actuators that uses electrical energy, it is the most common and it is the most correct. That means you can get a very you can get close to 100% for precision for electrical. That's what I'm talking about, and that's the one that you see most smaller devices use. For example, you don't see hydraulics being deployed in elevators. Neither do you see them deployed in medical equipment that require precision. Whenever precision is required, electrical is your go-to. But it doesn't come without its disadvantages. It's expensive, right? And there's a lot of environmental conditions as well. Of course, electricity has to be there for it to constantly perform its task. Advantages: it produces less noise. It is safe to use since there's no leakage. Yes, there are electrical leakages, but it doesn't lead to a total loss on the system. It can be reprogrammed. Like I mentioned, it has the highest control precision. The electricals might not be direct 220. Sometimes it's converted and stripped down currents, the little currents that you use, so it is not as dangerous as we used to think of it. Although there are industrial actuators that use the industrial current or industrial electricity itself, those ones are, there's a bit of risk involved with those ones. So those are the actuators I'm just going to look into. The next slide talks about the difference between sensors and actuators, and I've mentioned some already. That a sensor takes from the physical and turns it into electrical signal for data to be collected, while an actuator takes the data from electrical and converts it into a physical action. Okay, now if both a sensor and actuator is present, the sensor is the one that is at the input stage, while the actuator is the one that is at the output stage. Whenever they are together, usually the actuator receives information from the sensor to perform an action. Now, how sensors and actuators work together. The diagram you are looking at there, I hope everybody can see that diagram, tells you how that works. So a sensor at the beginning will measure the temperature. In this particular case, we're talking about, we're using temperature, the temperature sensor, and then it continuously would measure the temperature. The controller, which is the processor, the microcontroller itself, will be the one to process, and then whatever coding has been given to that processor will now be what the actuator will rely on. Okay, so if in this case the processor has been told that if the temperature gets to a certain range, turn on the fan. If not, leave the fan off. So whenever the temperature gets to that range, the controller reads it and tells the actuator, then the actuator turns on the fan and the fan starts working. So that's like a complete system, a temperature system. Another one here, how they all work together, is our normal, you remember our sprinkler system, the one we use in buildings. That's how it works. And what turns on the water is the actuator, but the whole process starts from the temperature being sensed by the sensor. So the sensor continuously reads the temperature of the room, then sends the signal to the controller. Remember, when we refer to our controller, we're talking about some of these things we've talked about before, the IoT gateway or the cloud itself, depending on where the sensor is connected to. Now the controller reads the signal and then gives an action or gives the directive to the sprinkler system, and the actuator turns on the water. That's what. That's how they come together to work. Okay, is there any confusion about this process I just talked about right now? How a sensor and actuator comes together. This is just a practical example, something I feel we should be able to connect to. There are so many other instances where the sensor and the actuator works. If you've ever been inside a car that is automated, I'm not talking about the autonomous cars now, a car that is the 20, let's say 2017, 2018, 2019, 2020 cars that has a lot of automation. Benz, for example, when you put in the key, those kind of Benz that use you slot in key and then you press a button to turn on. When you slot in the key, the Benz does what's called diagnostics. It will check all the system, and while it's checking that system, if they all pass, then the instruction is the engine turns on. So the actuator that actually turns on the engine is waiting for all the sensors in the car, both the one that checks the tire pressure, both the one that checks if your seat belt is on, both the one that checks. So after all of those are done, the controller has gotten the feedback and processed the data and say, okay, you are good to go. Then the car starts. Before now, or before the 2000s and the 2000s, yes, before the 2000s, if you mistakenly leave your key in the car and close the door, nothing goes wrong. Okay, Victor Taiwo is asking, what are the blue diagrams on the top of the arrow? I understand the middle one is the internet, but the other two I'm not sure. The first one there, that F, the F there is the temperature. Here is Fahrenheit, so that's just the unit of the temperature. The other one by the right hand side is just the sign for the actuator. I hope that answers your question. Okay, I was talking about the cars. So in the older model of cars, you don't worry about locking your key in the car. Why? Because the cars don't lock automatically. So when you close the door, the key is inside the car, you can still open the door. But then that button that you press down to lock the door, that manual button by the door that you press down to lock the door, once that button is pressed down and you bang the door, that door has to be broken into, right? That's for the older model. Now when the newer model started coming in, those Toyota cars, those new cars that you close the door, after a couple of seconds the door will pin itself, that presented a level of problem that if you mistakenly lock your key inside, if you don't leave your key inside and close the door, after a few seconds the key will lock. And then when that issue was noticed, car production companies started building sensors into the key lock, that keyhole, the ignition hole itself, so that when the key is still in the ignition, even if the car is off or on, the door will not lock itself. Or else your car could be on, or your car is off and you're just standing outside, and then the door locks you outside. So the sensors in that keyhole started communicating with the key itself. Okay, so you see, problem, solution, solution, problem. Now moving on, you understand now that systems are being built that will understand the environment, and some of these interactions will require an actuator. So for your door to lock, an actuator has to pull those levers that lock the door. So these are sensors that are communicating with actuators, and actuators taking place. I don't think anybody here would not understand the concept of that sound you hear in the car when the seatbelt is not on. It's an annoying sound. It keeps beeping as if the car is about to blow up. There's a sensor in the belt holder, that particular thing that you key in the seatbelt into. There's a sensor there that gets noticed when that notices the plug-in of that metal that you put there. Have you ever tried putting something else there to see if that thing will shut up? Now these are sensors that rely on other things, reading the environment. So when you key in that metal into it, the sensor reads it and the sound stops. Even when you press that button down, there's a button that helps you release the belt. Even when you press that button down, the sensor is not respecting that pressing of the button. The sensor is inside, so you must fix something inside that place for it to work. Okay, and then if that sensor is linked to the car starting, of course you know what's happening. The same thing that happens with automatic cars. All automatic cars, you put your leg on the brake to get an action going. You put your car on park. Before it can enter that park, you must put your leg on brake. All these are little sensors and actuators that are going on in our own environment. So that's how sensors and actuators work together. Do we have any questions on this particular session before I move on to another session? The next session we're looking at is embedded systems. Do we understand now how sensors and actuators work? We encounter this on our daily life, on daily basis. Okay, so let's move forward. Embedded systems. We're looking at embedded systems. Embedded systems is just talking about a combination of computer hardware or hardware and software designed to perform a task. That's what your embedded system is all about. They are using the word embedded to understand that they are all intertwined into one particular device. They are buried inside others. So industrial machines, consumer electronics, agricultural and processing devices, automobiles, medical equipment, cameras, digital watches, all of this are places where you find embedded systems. All these are devices we use all have embedded systems in it. If we are to break it apart, you understand that there are certain systems that handle certain things. Now by the time we bring it all together, let me give you a practical example. Your mobile phone. Your mobile phone is a combination of a lot of other systems. If you open the board of that phone, you see that there are smaller boards or diodes or whatever it is that make up the entire phone itself. So that's the embedded systems we're talking about. They may function within a larger system, or they could be providing a specific function by themselves. They can be programmed. That means you can change whatever it's doing, or it could be a fixed function. It could just be serving one purpose alone. The examples I have here are the practical examples, the most practical examples. Automobiles, the mobile phones, and the medical equipment. Your car, these new modern cars are the best practical explanation for what an embedded system is. The car itself is made up of too many things to begin to count, all working together to give you that seamless comfort. Okay, you have more than over 100 systems working together, from the brake system to the gear system to the ignition to the sensors in the car to the seat belt to the door locking and so on and so forth. All of these are embedded systems. Okay, even the cruise control, ABS, suspension control, navigation systems, airbags, all of this are systems of their own. Mobile phones as well are other examples of embedded systems. There's a system responsible for cameras, microphone, the connection, the power connection, operating system. All of these are embedded systems. Medical equipment as well. I can't begin to mention. There are so many of them. Now, how an embedded system works, I mentioned it before. It always functions as part of a complete device. That's what the term embedded means. The idea behind it being embedded into others is the fact that they are low cost, low power consuming small computers. So smaller computers that can be attached in, that can perform small functions to achieve some greater function. Okay, so generally they comprise a processor, a power supply, and memory and communication ports. Those are the primary things we are referring to. Okay. You said you didn't hear me when I started the embedded systems. Okay, okay. I think I'll let me revisit that. I'll revisit that right now. Okay. I started with the talking about the embedded systems and how they perform. I mentioned that the embedded system is a system of systems, smaller systems that perform specific functions and then collectively performing a greater function. And I mentioned so many examples like you get in a car. So the system that handles the brakes, the one most people understand as ABS, automatic brake system, it's one system of its own that's part of the collective. For example, the system that's responsible for shutting the door, pinning down the door a couple of minutes after you close the door and start the car. There's a particular system that after a while all your doors will shut. That system is a smaller system embedded in a bigger system that performs that specific task. Or the button you press to wind down the glass, that's another system of its own, performing its own function, have its own microcontrollers, and so on and so forth. So an embedded system is a combination of computer hardware and software designed for a specific function. That function can be changeable. That's why it's called programmable. It can be programmable or it could have a fixed function. Do we understand that? Do you understand my current explanation? Have everybody gotten this now? Let's be sure we're on the same page. Okay, okay. And then I mentioned examples of embedded systems. I talked about the automobiles. I've given you so many examples about the automobile systems now. And then mobile phones and medical equipment. Have you ever tried out the gesture based camera? There's a function that's called the gesture based camera. iPhone users know about it. Samsung users know about it. I don't know about other phones. But you set your phone camera to see a gesture from you and take a picture. So you can keep that phone very far and just wave at it and it will snap. That function of the camera is an embedded system of its own that uses a sensor to sense an action. Okay, that's true. Jude is saying when you smile. Yes, that's also a function that it has been programmed that when he sees a smile, it performs the action. And that action is taking a picture. So these are all smaller embedded systems, programmable, that can perform actions. Okay, and then I mentioned that there are tons of them in the medical industry. So many of them. One system having different embedded systems. So I went ahead to start talking about how the embedded system works. That the concept, the reason why they break it down into different systems is to get the low cost, low power consumption. Imagine if I'm able to change my camera when I want to, my phone camera when I want to. Imagine if I'm able to suddenly just swap a part of my car and change it for something else. That's what you get with an embedded system. So when my winder, the one that controls the winding down the glass up and down, when it gets spoiled, I'm not changing the entire car. It's just that component that I'm dealing with. When my phone camera has an issue and it's opened, it's just the camera section that is dealt with, not everything. Okay, so that helps you with the low cost type of a component, then low power consumption as well. So everything is not connected directly to the main line. They have their little demands of which it helps the entire system. Okay, so they are generally comprised of a processor, a power supply, and memory. Of course, there has to be some form of communication to communicate to other systems or to receive communication from other systems. The primary or basic characteristics of your embedded systems, you're looking at, it can be made up of hardware, software, and firmware. Sometimes there is just firmware and hardware, no software, but generally you have hardware, software, and firmware. Now, all of these characteristics I'm mentioning are orders. The main characteristics of embedded systems is that they are task specific. They perform a task. That's how you characterize embedded systems. But other ones can be this that you're looking at, consisting of hardware, software, and firmware. It can be a smaller thing embedded in a larger system to perform different tasks. It can either be a microprocessor based or microcontroller based. These are all terms you use in integrated circuits. It just gives the computer more power. Either it's a microprocessor or a microcontroller. And another one here is they are often used for sensing and real-time computing. This is where our IoT comes in. It can also vary in complexity and function. So this affects the type of software, firmware, and hardware they use. And the last one says they are often required to perform their function under a time constraint to keep a larger system functioning. So they usually have a time constraint in performing their duties. Okay, that's embedded systems. I hope we get the idea of what we're talking about. So, in terms of the entrepreneurial aspect of IoT, if you can create an embedded system, if you can have a little device, a little sensor connected to a board, or a little how will I put it, a little component that performs a task, you can have that embedded in an already existing system. So the security camera that has been installed in a house is okay, it's functioning okay, but the security camera is only using physical cameras, it's only viewing, it has nothing to do with motion, it has nothing to do with other sensors that we monitor. You can create a system that includes another kind of monitoring in the existing system. That's where the embedded system thing comes in handy. Okay, so moving on, do we have questions on this embedded system I just talked about before I jump to the next part of our task today? Is there any question? If there are questions, let's get them. If there are no questions, let me jump right into the last section of our task or our class today, so you understand what I mean by embedded systems. All of these things we're talking about is just sometimes we're giving name to what you already know. Now you know that your phone is made up of embedded systems, that the car is made up of embedded systems. Those different components function together for the collective good. So let's move forward to the last part of this, which is the cloud. I said it from the beginning that I won't dwell too much on this because we're going to talk about it practically in our class. We're going to introduce some cloud platforms to you, and then we're going to use a little bit of them. So I'm not going to be defining what cloud is. What I'm focusing on today is what's called the dynamically distributed cloud. It is one of the applications of cloud computing technologies which is used to interconnect data and applications which are served from varying geographical locations. Let me break that down for you. It's talking about the cloud as we know it, but served in different geographical locations to solve certain needs. Now, the basic principle or requirement behind dynamically distributed cloud is location, regulations, security, and redundancy. So the location first, to enable more responsive and performance service. If I want to connect to Denmark, I want to serve content to Denmark, and my site is hosted in Nigeria, it will be difficult for speed of people browsing my content from Denmark. But I can be in Nigeria and host my websites in a server in Denmark to give them close access to my resource. I can be in US, I'm trying to sell something to Nigerians, and instead of hosting in Nigeria in US, I'll host it and the cloud service will bring it closer to Nigeria so that Nigerians can access it very fast. That's what your dynamically. Denny is asking if it's VPN. No, it's not VPN. VPN is tunneling through the internet to a particular location, right? This one is bringing content close to you. Let me use physical example. Think about those persons who walk on the street. What they do is bringing products close to you. So you're in traffic and you see gala to buy. The real gala shop is far away, but the person that's bringing it close to you is making sure that it is easily accessible for you. Now that is what the dynamically distributed cloud is all about. It's dynamically distributed so that the resources it provides can be closest to the location. But with location comes regulations as well. For example, there are certain contents that are not allowed in certain geographical locations. For example, Facebook and the rest of them, they are banned in some places, right? So to be able to serve the regulations, to be able to meet with the laws of those places, those content has to be served there as well. So regulations which may require that data never leaves the user's country. So sometimes you have a content, and the rule of that content is that this content should never be seen or heard outside this country. So such content is served and made sure it doesn't exit that location. Security is also a part of it, a principle to ensure that certain data and processes remain within an enterprise. For example, some government offices. Most people know, or most people should know, that www that we type, the World Wide Web, the one we used to think or we feel like that's the internet, is just one application on the internet. So the ones that governments use, governments of different countries, the one they use that still function like the internet is different from the www. So with this dynamically distributed cloud, they can afford to have that kind of internet space in that location alone without it being moved or without being accessed by any other country or any other region. The last one they says redundancy. Beyond the provision of local, regional, and national site redundancy to sites mitigate large-scale outages. So that my site is hosted in Abuja and light in Abuja goes down does not mean the people in Lagos should not enjoy the services. I'm using sites because that's a typical example of how these things work. Okay, this is an example. An example of dynamically distributed cloud is a content delivery network. It delivers content close to the location, and one company that uses this is YouTube. YouTube uses what's called CDN. So the video you play, even if the person that uploaded it is in US. Can anybody hear me? Zainab says she cannot hear me anymore. Okay, so the YouTube you are watching, even though it's uploaded to from US, and even though the YouTube is based in US, the content you watch, as far as you have sought out that video, you have checked that video before, or you are just about viewing that video is deployed closer to where you're watching it, closer to Africa, closer to Nigeria, making it easier for you to watch that video without having to transverse the entire internet from here to US. That's why YouTube videos play faster than other videos you can see online, because they use content delivery network. So this is a diagram talking about how IoT has been related to dynamically distributed cloud. So you have Internet of Things. I remember I talked about edge computing. So the cloud is where those things are connected to, but let me use the word very far. The cloud is very far from you. So edge computing is you deploying a portion of the cloud to your own geographical location or to your own environment to make it faster to process. So it does the real-time data processing. That's how it works. This slide talks about relationship between edge computing and the cloud. It's just one of the implementations of distributed or dynamically distributed cloud. The last part of what we're talking about today is IoT security. Security in Internet of Things, it's a bit different. It's a bit difficult to get everybody to agree on one thing, because the things we're talking about is being used and produced by a lot of people. So security in IoT is not a it's not an ironclad. It's not something that is everybody can just agree to one thing. Okay, so on the IoT system, typically we can break it down into three parts: the device, the cellular infrastructure or network infrastructure, and the cloud platform. Now these are the three logical parts of the IoT system. Now we have to consider security in those three parts. For example, I'm not the one who's responsible for the security of the network I'm connected to. If I'm connected to MTN, so my device is connected to MTN to get to the cloud, MTN is responsible for the security of their network. The cloud platform I'm connected to is responsible for the security of that cloud platform, and the person I bought my device from is responsible for the security of the device. You get the gist. So all of these persons play a key role in security of IoT. God forbid I have my entire house connected and someone hacks my device, one device, and connects to the others, and the person can control how my window goes open, my light turns on, my heater turns on, my microwave starts working, my fridge orders for food, my gas in the kitchen turns on. That's the kind of implication we're looking at when there's a hack. So all of these platforms will have to come together, or would come together to generate the total security, the IoT security as it is. So it's not only about installing and activating a device or connecting to a network, but also managing the ongoing operations throughout their life cycle. So as far as my device is connected to that cellular network and connected to that cloud, there has to be some form of security going on. And then the entire security ecosystem is what you see here on this, where you have the device itself. From the moment the device turns on, there is secure boot available for the device, so nobody can hack into the device while it's booting, which is like the core thing that a hacker is looking for. If I can get into the device while it's coming on, I can gain control of the OS. So secure booting exists. And then you have the unique permanent module ID. It's unique. There's no two of them that's existing in the ecosystem, so that one cannot use one to get into the other. Then there's secure storage. There's trusted environment, execution environment. No code can run in to my device from outside my network or from outside the device. And then you have an integrated connection to the network. That's integrated SIM, providing you security for the device. And the next one is the infrastructure, the cellular infrastructure, the security for that one. Of course, we know that they go a long way in securing their environment as well, but there should be a secure transport between the device to the cellular network and to the cloud. The cloud themselves will provide security for the cloud. You always read about those securities before you adopt the platform you want to use. Don't worry, Zainab. I'm recording, so I would upload what I'm recording so that you can catch up. I apologize for the network problems. Okay, so now that brings an end to our virtual session, Internet of Things, connecting regular everyday thing or things or devices to the internet, and not just connecting it, making life easier by having control over the internet or over a network. Okay, so my question is this: from the beginning up until today, can anyone point out where or which part of a class that is so confusing to them that will require us to include in our physical class? Because yes, I mentioned that we want you to understand everything, but then we are streaming our physical class to the very essential things. But I cannot jump everything I've taught so far when someone has not understood some part of it. So what part of everything we've been talking about from the beginning till now is still seeming like magic, so that I can include that in our physical class? I'm going to prepare an evaluation, a post evaluation of the topics we've had so far, and then I'll send it across. You fill it for me, and then I can use that to detect which sessions. I know I talked about the club session we're going to handle in the physical class, the networking session we're going to have in the physical class. Those two, I'm not going to include them in the post evaluation because I know I'm going to talk about them in the physical class. We're going to do the practicals, so I'll save those ones for those times. So, do we have any questions so far? Do we have any questions? Uh, Day one introduction, we looked at the beginning, the definition of what IoT is, introduction to Internet of Things. We defined the Internet of Things. We looked at why IoT is important, and then we talked about receiving and acting on information, collecting and sending information. That's the categories of things connected to the internet: the things that can collect, the things that can receive and act on it, and things that can do both. We talked about those ones, and then we mentioned a few bit of why we are taking the course, and then we moved on to the next class when we talked about the history of IoT, how we all started, and then we moved on from day 2 to day 3 where we talked about governing bodies, IoT standards, derived qualities of modern IoT, the framework for IoT itself. Then day 4 we looked at how the internet works, the major IoT building blocks, the architecture and reference models. On day 5 we looked at networks, types of networks, the OSI model, networks and connectivity. Day 6 we talked about internet protocol. Okay, somebody said day 8. Okay, so day 6 we talked about internet protocol. Day 7 we looked at common elements of IoT. We started with the first one, which is the sensing and embedded components. Then day 8 that Samuel talked about, we talked about the next one, which was connectivity. When we talked about the cellular, satellite, Wi-Fi. Since we're dealing with the networking class, you get more on that when we do our physical class. I need you to make sure you don't forget this. This is like something new. This is the only new thing in everything here. We already know satellite, cellular, Wi-Fi, Bluetooth is the LPWAN that we introduced there. We would mention some physical examples or some examples later on where you start hearing things like Zigbee. Okay, then day 9 we looked at the last part of this, that's data processing. Okay, second to the last, which is data processing, where we talked about some cloud understanding or some cloud platforms and how they interpret data. Then day 10, which was the one my colleague handled, networking and connectivity medium, where we talked about wireless sensor networks, wireless LAN. Yes, wireless sensor networks, and so on and so forth. Okay, we'll talk about that one. It's part of They're all part of networking. Then day 11, we looked at 4G and 5G and 4G LTE. And then today we talked about embedded devices and actuators, and then dynamically distributed cloud and IoT. So when I send the feedback to you, please do well to fill it and then let me know so that we can plan for our physical class. So are there questions? Is there questions you have for me to handle today? If there are questions, let's get it. If there are no questions, let me get how you feel about the class we've had so far, the virtual class in general, and then while we prepare for the physical class, which will take place in exactly two, is it 2 weeks or 1 week plus? Today is 20, today is 21st, so the classes are to start in Monday of 2 weeks time. If there are no questions, it means this is where we end our virtual class before the physical class. I'm yet to know if, yes, on the 30th, I'm yet to get feedback if there will be a virtual class after the physical class. But the physical class was supposed to end it. But what we intend to do is to keep an open channel so that implementation, as time goes on, as you try to implement what you have learned, we'll keep an open channel so that when you need help, you let us know. We provide the help to you as we can. When you are venturing into a place you don't fully understand, we can venture into it together and see how we can move Nigeria forward, see how we can develop the country better. So thank you very much for being with me for the entire time. We've had 2 weeks of IoT. So thank you very much for always with the 2 weeks or 3 weeks. I've had a good class. I have so many of my very punctual students. They are always there. They will always be around. They will always keep me on my toes. Joy, Mr. Francis is always here. Mr. Victor, Zainab, Ajoke, Victor, Sunday, Samuel, Mr. Jude, Adebisi Mumin, Adewale Ahmed, Samuel Damilari, Emmanuel, you weren't so consistent because the name is not so. I hope you picked up a few things. Peace Ebenezer, thank you for always being there. Opeyemi, yes, I can't forget that name. Tony as well. Ola Abraham, I think one or two persons are missing. I'm turning on the mic, so if there's something you want to say as we sign out, I'm all ears. So thank you very much for. Okay, DBC say he has a question. I think I turned on your mic. Hello, Mumin. Can you hear me? Hello, can you hear me? Can anybody hear me? Okay, so you said you have a question. Can we get your question?
Good afternoon, sir.
Yeah, good afternoon.
First of all, let me appreciate you for your time, for your lectures.
Thank you too.
Let me speak for myself, but I can see the reaction that you really appreciate the class and you've been so good.
You're welcome.
First of all is let me okay now. I made a request and I think you asked me for the link, so I haven't gotten feedback.
Based on the mail you sent. Okay.
Yes, yes. So that is number one. And number two, I think there is need, and it is very important for you to emphasize what your colleague and the class he handed that day,
Yeah,
because the slide wasn't changing, and what we were not that free flowing in class.
I
So
understand.
that class need to like revisit on that.
I
So that is
understand.
also important.
I understand.
So
You're welcome. I understand. Like I said, it's the physical class has a networking session. So he's going to break down the entire networking related to IoT and basic networking. So we're not leaving that away. We're going to handle it. Please, if you are the one that's in an environment where children are talking, can you please mute yourself? Okay, so if there are no other questions, okay, Francis wants to ask a question. Mr. Francis. Mr. Francis, are you with me? Hello, Mr. Francis, are you with us? It seems he's away from the mic. Hello, Mr. Francis. Okay, I think he's off. Yes, the location will be sent across to me, and then I'll forward same to the platform. I don't know what arrangements that they are making so far, but I think they are not planning for you guys to be traveling from your own destination to the class. I can't confirm the arrangements they are making for now, but I don't think it's right for them to be talking about you coming from your own different parts of Lagos to the class. Probably they will make arrangements for where students will stay. I'll have to confirm that and get back to you guys. I know Lagos is very vast, so I don't know how they're going to plan that out. But so when I get the information for the physical location, I'll pass that across. In fact, whatever information I get pertaining to the physical class, I'll pass that message across. With the traffic and the way things are jammed in Lagos, I don't think we are expected to be moving around like that on everyday basis. Like you come in the morning, go in the evening. It might be too tasking. But don't listen to me yet until I get the proper information. Then I'll pass it across. That's just me feeling like it would be difficult to have such a class and then have people transverse the entire Lagos just to get to the destination. So thank you very much for joining me today. I've taken a lot of your time. I've taken almost another 15-20 minutes of your time. I apologize for the network problems that I've been facing. I think this will be the last day we will have network issue. The next time we're seeing, we should be in a physical place that network will not disturb us. So thank you very much. It's been nice having you guys. I hope to see your faces very soon. So see you in class. Yes, next week.